Log on, tune in, find out. Another good idea from Cambridge.
By a former member of Cambridge University, Christof Sparber, will talk about Bohmian measure and their class.
Thank you. Of course, I want to thank Peter and Jin for the invitation back here. I'm happy to be back in Cambridge for a little while. So what I'm going to talk about is basically will be basically a review of results which we obtained together with Peter and Thierry Paul in the last 1.5 years or so on a subject that we have been interested sort of for more than 10 years already. It's a semi-classical quantum mechanics, but it is so this time it comes sort of with a bit of a new twist. So this is the outline of my talk. So okay, I will of course present to you the basic setting and tell you what the word Bohmian mechanics or what that should actually be, which is maybe something that not everybody knows. And I should then go on and present what we call Bohmian measures with some definitions and basic properties. And as we shall see, it will be rather natural to compare these kind of measures to something that is maybe much better known in this community, namely the Wigner measures. And finally, we shall talk about a particular case of semi-classical wave packets, which you have already seen also in Rémi's talk yesterday. Okay, so basic settings. So let me set the stage here for what we're going to do. So we take our beloved linear Schrödinger equation in the scaling that we have seen already several times during this conference, namely in the semi-classical scaling. So all physical parameters are rescaled in a dimensionless form so that they are 1, except for one epsilon, which is the small semi-classical parameter or the scaled Planck's constant. So it appears, so it comes basically with every derivative. So there's an epsilon squared in front of the Laplacian and an epsilon in front of the time derivative. There's an external potential here. And yeah, clearly the wave function is on L2 over Rd. And so what I will do here, or assume throughout the talk, is that the potential is smooth and say bounded. This is a bit too much I mean, we can do better, but just for the sake of simplicity, assume that you have a nice bounded potential, so that you, first of all, what this tells you is, of course, that you have a unique solution of the Schrödinger equation for all times t. And let me recall to you the two main conservation laws, namely the conservation of mass, or L2 norm, as well as the conservation of the total energy, which is the sum of the kinetic and the potential energy here. Notice maybe that the kinetic energy, due to the scaling of the equation, comes with an epsilon squared. Okay. And then what we shall assume from now on is that my initial wave function is in L2 is normalized to 1, which is the standard normalization. And I shall also assume that I have a uniform in epsilon, that is, a uniform bound on the initial energy. This implies, in particular, that for all times t, my wave function satisfies the following uniform bound, namely I have a uniform bound in L2, right, due to this conservation, and also due to the energy conservation. I also have a uniform in epsilon bound of not the gradient, but epsilon times the gradient. So this property I shall refer to as psi being epsilon oscillatory. That is a term that actually can also be defined a bit more general, but you think of it like this. So this is what we're going to assume. These are rather natural assumptions from the physical point of view. It basically tells you that, I mean, for any epsilon, you want to have a uniform bound on the energy, and that sort of tells you that there is a certain, epsilon wavelengths of oscillations in the solution of the Schrödinger equation. Okay, fine. Now, in quantum mechanics, the psi is used to define densities which correspond to physical observables, and I shall heavily rely on the two maybe most important ones, namely the position density, which is just the modulus of psi squared, and the current density, which is given like so. And of course it's well known, and we have seen it already in Ansgar's talk, that if psi solves the Schrödinger equation, you at least formally immediately derive the following system for rho and j, which is typically referred to as the quantum hydrodynamic system, which is an Euler equation with a third order perturbation of third order derivative on the right hand side here. And it is known in particular that for wave functions which are sufficiently smooth, every term in this system is well defined in the sense of distribution. That's an old result of Ingo and Peter. So I will use this system in a minute. But before, let me tell you, okay, let's go, so all I was telling so far is a classical textbook quantum mechanics. Now, what we shall do here is study this from the point of view of Bohmian mechanics. Now, what is Bohmian mechanics? It is a reformulation, if you want to say so, of quantum mechanics. So it has been invented or discovered by David Bohm in '52, which, so in an attempt to formulate quantum mechanics in a way that allows you to still keep the concept of particle trajectories. Namely, what does he do? He says, so you solve your Schrödinger equation, so you can do this, and this gives you the psi wave function field for all t and x. So this is now a given field, and what you do with it is the following. You define a flow map, capital X epsilon of t, so which associates to every point x the corresponding time-dependent capital X epsilon, by the following ODE, so x dot, so this is just a time derivative, of course, equals a velocity field u, which is defined by the ratio of the current over the particle densities. So formally this is just given by this. And in addition, you assume that the initial data, small x, you don't know it precisely, but you only know its distribution, which is just given by the initial position density psi 0 squared. Now, that is sort of in a nutshell what Bohmian mechanics does. And let me say that, okay, so I mean, from the point of view of physics, this can in general lead to, well, I would say some heated discussions between physicists if or if not this is a legitimate reformulation of quantum mechanics. We don't want to get into this. I should maybe say just two comments. First comment, as far as I know, this reformulation has never been experimentally falsified. So from that, so that is at least to my knowledge. So it is not. So from that point, so in that sense, one could say it is a legitimate point of view. But for us, what we are actually interested here is more the conceptual. It's more a conceptual bridge between classical and quantum mechanics, in the sense that it will allow us to smoothly, more or less, pass from classical to quantum mechanics due to the fact that we can rely on this trajectory picture, and this is sort of what we are mainly interested. Okay, and to do this, I shall reformulate this point of view, which you can call the Eulerian point of view of Bohmian mechanics, in a Lagrangian framework. So yeah, maybe I should say the following first. Of course, here, this is all very formal, right? I mean, you see that immediately that when psi is 0 here, this might be bad, because you divide here by psi. So I mean, in general, this velocity field u is well, certainly not Lipschitz. In fact, it's not even BV. Nevertheless, it can be proved rigorously. There is a paper by Berndl and co-workers, but there are several other papers in that direction by Stefan Teufel and other people that proved the following. So this flow map, capital X epsilon of t, is in fact well defined, rho 0 almost everywhere. And for every time t, the full quantum mechanical position density can be obtained as the push forward of the initial position density under this flow map X epsilon of t. So this notation here, this push forward, is nothing but, I mean, in full detail, what is written down here. So for every test function sigma, the following identity holds. And this is also often referred to as the equivariance of the measure rho epsilon of t. So even though you might say at the first glance this velocity field is much too singular to make sense, in fact you can give sense to it, and you can obtain the full quantum mechanical position density as the push forward of this initial measure. Fine. Now that is, as I said, the Eulerian point of view of Bohmian mechanics. Now let me reformulate this in a Lagrangian framework, at least formally, by defining a velocity or momentum variable capital P epsilon, like so, and try to get an equation for it. So we write P dot, which is just ddu, right, since x is this. So I compute this. So it's just a partial derivative, of course, with respect to time, plus the gradient with respect to capital X times x dot, and x dot is u. I get this terms here, and then I use the quantum hydrodynamic system I've just shown you 2 or 3 slides before, rewritten in terms of u. I just plug it in, and what I end up with is the following phase space formulation of Bohmian mechanics, namely x dot equal to p, and p dot equal to minus the gradient of potential, which is given as 2 terms, just the external potential, just as the classical force term, so to say, minus now something that encodes the quantum nature of the problem, minus the gradient of this epsilon dependent potential, which is well known and which is just a so-called Bohm potential. And the initial data, of course, I have to prescribe is small x and small u0 epsilon of x. And so this, so notice here maybe that in this term, right, there's an epsilon squared here. So this here, at least formally, can be derived, and now of course looks sort of very familiar, because clearly this system here, well, provides a non-local, this system here looks very familiar because it looks like a perturbation of the classical Hamiltonian phase space ODEs, right? Because, I mean, perturbation, at least formally, because I have an epsilon squared here, so formally this term here is small with respect to this term here. So in other words, so this system, as it says, provides a non-local perturbation of the classical Hamiltonian phase space flow. Why non-local? Well, non-local because, of course, strictly speaking, in order to compute the Bohm potential, I have to compute this Laplacian of the square root of the density over the density. So, I mean, strictly speaking, I have to compute this for all x and t. Right? So this is, I mean, a bit of a, I mean, this is sort of like, if you want to think of it almost like a Vlasov type non-local term, just that it is much more singular, right? You don't convolute anything with a nice kernel or something. But it is sort of similar in spirit. So, okay, so this is the system, provides a non-local perturbation. Of course, formally, at least converges in the classical limit epsilon to 0 to the classical Hamiltonian phase space flow. Is in fact, and this has been one of the motivations how we actually came into this business, is used by quantum chemists to compute multi-particle molecular dynamics. So there's just one reference here. So, I mean, this is sort of why do quantum chemists like this? Well, say you want to compute molecular dynamics. You have lots of particles. Some of them are very heavy. They are almost sort of, say, classical. Some of them are lighter and hence more quantum dynamically driven. So, and you want to compute this effectively on sort of in a unified way. And what you like to do, of course, what these people like to do is put the Monte Carlo code and basically compute these trajectories, and you can roughly speaking, you can then choose, depending on how big you choose the epsilon, to either compute the particle trajectories quantum mechanically, so to speak, or just evolve them by the classical flow. And this all goes under a nice, at least formally under a nice conceptual, all-in-one sort of nice language. Of course, it's not so simple, right? Computing this term here, gradient of Laplacian square root of rho over rho, will in general be a mess. And this is sort of where all the difficulty goes into, but at least sort of conceptually, it looks appealing from the numerical point of view in order to do multi-particle dynamics. Moreover, as we shall see, it also allows us to compare this, that I will do now in the next 20 minutes, to compare these Bohmian mechanics to the much better theory of Wigner functions, which are also, of course, based in phase space. And finally, but this is sort of more a conjecture of us, it could provide a starting point for an optimal mass transportation formulation of quantum mechanics. Okay, I should get to this maybe also in a minute. Okay, but the first thing I should do now is to make this formal derivation rigorous and give actual sense in a mathematical sense to this phase space flow. And this I will do by defining what we call a Bohmian measure. So here's the definition. So you give yourself a scale epsilon and a wave function, which is sufficiently smooth, and of course you compute from it the associated densities rho epsilon and j epsilon. Then you define the Bohmian measure beta epsilon, which is a positive measure on phase space, by the following operation, or if you want a bit more formal, the Bohmian measure is nothing but a monokinetic, so sorry, there's an epsilon missing here on top of this rho. So there's a monokinetic measure on phase space where the momentum is just concentrated on the quantum mechanical velocity field. Now notice that this makes perfect sense even at points where rho is 0, because this phi here is of course a test function which is smooth and decays at infinity, and where rho is 0, this here is bounded, and I multiply anyway by rho, so this here, this makes perfect sense. So this is my class of phase space measures, and as just as a sort of byproduct, of course, formally what these measures do is they define you what is called the Lagrangian submanifold on phase space. Of course, this has to be taken with a grain of salt, because I can actually not do this here pointwise, right? P equal u of epsilon, because this here is not defined pointwise due to nodes of wave functions. It's only defined rho almost everywhere. But morally speaking, this is what you do. So here's the first. Okay, so basic properties, of course, of these measures are that if you take the zeros and first moment with respect to p, you just get back the quantum mechanical position and current density, just as in classical kinetic theory. One should be careful, though, with this, not to think that everything is completely analogous. In particular, if you compute the second moment, or p squared half of beta, so you compute this is just given in this form. This, however, is not equal to the full quantum mechanical kinetic energy, in contrast to classical dynamics, right? Because if you compute the full quantum mechanical kinetic energy, which is defined like so, you rewrite it in terms of j and rho, you see that it's actually two terms, and only the first one you can capture from the beta. The second one you are missing. The second one, which comes also is again formally an O of epsilon squared perturbation of this term. Okay, but okay, so I mean, if you're, as long as you're satisfied with the first two moments, they are in there. And moreover, this measure, in fact, can be used to rigorously define this phase-space dynamics. So let me call capital phi epsilon t the phase-space mapping of this flow, of this sort of phase-space flow that I showed you before. And so the lemma is that, in fact, this mapping exists globally in time for almost all x and p relative to this initial Bohmian measure. And okay, it's continuous in time on its maximal open domain. And in addition, for any time t, the beta epsilon of t can be obtained as the push forward of this initial monokinetic measure under this phase-space flow. Okay, so this sort of gives a rigorous sense to this Bohmian trajectories in phase space, at least, I mean, beta epsilon 0 almost everywhere, so to say. Okay, fine. So now that we have this, I mean, okay, so in particular, I mean, what does this tell you here? This equivariance property for beta epsilon of t basically allows you to interpret beta epsilon as a weak, very weak, in fact, solution of the following Vlasov type equation, right? I mean, you just by, I mean, just by identifying the flow I've showed you before as identifying it as a characteristic flow of an associated first order PDE, you find this Vlasov type equation, which now looks again familiar because it looks like your like a perturbation O of epsilon squared, nonlinear perturbation, in fact, of the standard Liouville equation on phase space. So notice, I mean, this is really truly nonlinear, right? Because I have to compute the Bohmian, so that the fourth term, the Bohmian potential from beta by integrating out the momentum variable. And so at least again formally, clearly if you plug in beta in this monokinetic form, you see that this is formally equivalent to quantum hydrodynamics and hence also formally equivalent to the Schrödinger equation. Okay, and that is also why, which maybe as just as a side remark, why we thought that this could be a starting point for mass optimal mass transportation formulation, because I mean in the homogeneous case, so where you drop the sort of this term here, and okay, so you drop also the external potential. So if in a purely diffusive setting, this type of PDEs have already been analyzed by Ansgar and also by other people using Wasserstein techniques and so on. So maybe if you can combine these techniques with Hamiltonian dynamics, maybe you can give a sense to this in a optimal mass transportation framework. Here, what we only do is just sort of give sense to it or just provide you with the fact that indeed this equation makes sense. Say, right? I mean, just because I have this property here, this push forward, does not mean that actually all of these terms here are well defined, in particular, of course, the nonlinear term. But they are, and this is sort of the first theorem which we proved recently, I mean, under sufficient regularity on the initial data and the potential, of course, for any epsilon, you can show that, in fact, the Bohmian measure beta epsilon is indeed a weak solution of this PDE in D prime, if you want. The point being, of course, that what you have to do is work a bit to give sense to this, well, rather nonlinear. I mean, there's also gradient x here, okay? So this rather nonlinear term here as a distribution. This is not completely obvious and straightforward, but you can do it, I mean, in particular using the push-forward property and some a priori estimates. Okay, so in other words, what this tells you is that this, if you give yourself a psi, a wave function solving the Schrödinger equation, if it's sufficiently regular, in fact, each of these, I mean, or this equation here makes sense. Okay, fine. Now on to the classical limit, right? I mean, all of this, as I said, we consider it as a nice bridge, so bridging quantum mechanics and classical mechanics, because it sort of allows for a reformulation of quantum dynamics in a phase-space framework, including, in particular, and in contrast to the Wigner theory, including trajectories. And so this looks nice, and of course looks as if you could sort of easily make the transition from classical to quantum mechanics. And so what we shall discuss now in the following is the classical limit of these measures as epsilon tends to 0. Clearly, I mean, just passing to the limit formally here will in general not be correct, because this is a highly nonlinear term. So I mean, you would need a lot of a priori estimates and compactness to do so, which in general you cannot. So, but nevertheless, so let's start with the theory. So in fact, so if psi epsilon is epsilon oscillatory, and I've written here again what this means, then what you can show that there always exists, well, up to extraction of subsequence, there exists a limiting measure beta, so that, I mean, a classical limit, so to say, which is a non-negative phase-space measure, so that you have the existence of a classical limit. And in addition, you know that this classical phase-space measure beta incorporates the true classical limit of the first, I mean, of the position and the current density. So in particular, I mean, just by taking the zeros and the first moment. So in other words, this object, this limiting measure beta here, yeah, as it incorporates for all times t the classical limit of rho epsilon and j epsilon. And okay, right, there is also there's an additional remark, of course, if there you have some more tightness. In fact, you also basically can integrate in x and interchange limit and integration, so that you do not lose any mass. So okay, so this is sort of analogous to the Wigner measure theory. Now, as I mentioned, the word Wigner measure, of course, I mean, what we are now would be interested, of course, is to know more about this beta, right? I mean, we don't have an equation for this, because we cannot simply, from this weak convergence result here, or weak star convergence result, it's not sufficient to pass to the limit in this equation, right? I mean, this term here is this nonlinear term. I cannot just pass to the limit in it. And so it is not so easy to get more information on the limit beta. And in particular, for example, a natural question seems to be, can you say, can you make sure that this limiting beta will again be monokinetic? Because, I mean, you started with a monokinetic measure per definition. Is the limit also monokinetic? So to speak, do you stay on the Lagrangian manifold? And moreover, of course, what we would be particularly interested is can we in fact infer something from beta on the classical limit of these trajectories? Well, you might say, why not study the classical limit of these trajectories from the beginning, right, and just forget about the beta? Well, the honest answer is that this is just a bit too hard. We can't do it. We can do something on this beta, and so this is sort of why we take this route. Okay, so and in order to do so, in order to gain some information on this limit, what we did in this paper, which is published in Journal of Functional Analysis now, is what we did is we tried to give a characterization, or try to invoke the theory of Young measures in order to study this limit. So here it's just, I mean, here it's just, I recalled for those of you who don't know it, the definition of a Young measure. So you give yourself a family of functions f epsilon, and then there exists a measure mu parameterized in X called the Young measure with the following two properties. This X mapping on this mu is measurable for all test functions, and in fact for any test function sigma in L1 you can compute the limit as epsilon tends to 0 of this quantity here by integrating over this Young measure, right? And I mean, you see the left-hand side already looks a bit like the Bohmian measure. I mean, the action of a Bohmian measure. Okay, so by doing this and invoking, I mean, then more classical measure theoretic results. So here is, for example, a first technical lemma, which tells you the following. So you give yourself a nice wave function. Then in fact there exists a Young measure mu x on say momentum space cross some one-dimensional sort of auxiliary variable, such that the limiting measure, the limiting Bohmian measure can always be well, it's at least larger or equal to this d plus 1 say in 2 dimension in 1 dimension the second moment of this Young measure. And if in addition you know that the particle density converges weakly in L1, in fact you have inequality, and then this here is indeed a probability measure. So I mean, this of course may not say too much to you now, but I mean, it's just sort of, I wanted just to outline how we try to get some information on this beta by invoking somehow this, well, rather well-developed theory of Young measures. So in particular, for example, you can prove the following theorem. So if you have, so to speak, strong convergence of the particle density and at least in measure convergence of the current density. So what does that mean? So it means that the measure, so measure here always refers to the Lebesgue measure. The Lebesgue measure of this set as epsilon tends to 0 is 0, then in fact you know that beta is just a monokinetic phase space measure. So this is this theorem gives you a sufficient condition, or so to say, to conclude that the beta stays sort of that the limit again is a defined Lagrangian manifold. Okay, this is maybe all a bit technical, and I should rather maybe make a comparison to something that is much better known in this audience, namely the Wigner transforms. And of course I can be very quick here because we have seen this already in the conference. So just to fix notation, so here I define my Wigner transform of associated to my wave function in the usual way, right? I mean, epsilon scaled Wigner transform. And yeah, I recall to you that as before, we know that there exists a limiting measure called the Wigner measure up to extraction of subsequences, where the limit is here in this weak star sense. Good news is that one can identify this limit by solving a PDE, namely the classical Liouville equation, since it can be shown that this thing here, which by the way is also non-negative, is in fact the distributional solution to this equation. And just as before, I mean, if the psi is epsilon oscillatory, you can get the classical limit of the position and current density by taking moments, and even more. I mean, for every sort of sufficiently smooth or well-behaved quantum mechanical observable, every expectation value, right, of the observable A, so the operator associated to my classical phase space symbol. So here this is my quantum mechanical observable. So every expectation value in the state psi epsilon, its classical limit can be obtained by integrating the classical symbol of the observable against the Wigner measure, so the limiting measure, right? So that's sort of this is of course a well-known fact, and sort of what this tells us is that more or less that this limiting Wigner measure is, so to say, the correct classical limit. It incorporates all information for all possible, observables under some sufficient regularity and so on. So the natural question is, when do we know if W equals to beta? So there are some results which we can prove on this connection of W and beta. So okay, let me neglect the time dependence here for the sake of notation. So here's the first result, which is sort of the subcritical case. Say if psi is uniformly bounded in L2, and if in addition so that the epsilon gradient goes to 0, then what you can prove, in particular by invoking these Young measure results that I've shown you before, what you can easily prove is that W equals to beta equals to this measure here. So, what does this tell you? It tells you that for wave functions which do not oscillate on the scale epsilon, but maybe on some larger scale, right? They do not oscillate on the scale epsilon since this limit here is 0. In fact, both the Wigner and the Bohm measure are the same and look like so. So that is good because it tells you that at least, these two limiting measures sort of, they see the same kind of epsilon scales. Okay, so a bit more interesting now, let's incorporate an epsilon oscillatory scale here. Let me write my wave function in this form, which I can always do. Notice that here I have S epsilon and rho epsilon. And then I can give you a sufficient condition which ensures that a monokinetic Bohmian measure is in fact equal to the Wigner measure. So say if psi epsilon is epsilon oscillatory, and if you have strong convergence of this particle density, and if in addition, well, we have several formulations, I just give one of them here. So if in addition there is a limiting phase, so to say, such that this limit exists, so sorry, that should be equal to 0 here. So this limit, of course, is equal to 0. Then the Wigner measure is equal to beta is equal to this monokinetic phase space measure, which is something that for the experts, of course, is clear, has a clear connection to WKB approximation. So this theorem basically tells you that before caustics, everything is fine. The beta is in fact equal to the Wigner measure and is equal to this well-known form. Bit more general though. In fact, in general, neither the Wigner measure nor the limiting Bohm measure will be monokinetic, and you may still want to know something on if they can be equal or not. So here is the most general theorem we could prove, namely, if you have that this quantity epsilon gradient square root of rho goes to 0 in L2 log, I recall to you that this was just the term, right, that was sort of in the quantum mechanical kinetic energy, which is this J squared over rho, epsilon plus epsilon squared gradient square root of rho. This is the kinetic energy. So in other words, if you know that this perturbation in fact goes to 0, and if in addition this Hessian, scaled Hessian in L infinity basically goes to 0, then again you get that the limit of the Wigner function and the limit is equal to the limit of the Bohmian measure. So this is in fact what is interesting is that this result we can show it to be almost sharp, in the sense that this condition here is a bit too general. If you would allow me to give a stronger a priori estimates on psi epsilon, say there, if you allow me to put some sort of second order epsilon oscillatory condition on it, then you could see, then you could prove that basically this result is sharp. Okay, so well, I mean, all of these results, they somehow give sufficient conditions on equality for the limiting measures. You might say, well, in general, it will be hard to check if these conditions are sort of satisfied. And in order to have sort of a better feeling, maybe one can just do some simple examples. So let's do that. Let me start with the following basic example. So assume that I give you a wave function which is of this form, so some slowly varying amplitude f of x times some periodic function g of x over epsilon, so some gamma periodic function. So in particular, I mean, this is sort of any WKB state is of this form, but I mean, this is of clearly more general. So gamma, I mean, gamma here is just some regular lattice. I mean, take it 2 pi periodic or 1 periodic, what you want. Then what you can prove, in fact, is that, I mean, you can compute the limiting measures here explicitly, or semi-explicitly, of course, up to f and g, which you don't know exactly, but I mean, you can prove them, you can compute them explicitly, and what you can prove is that they are equal if and only if g is given in this form, namely, so to say, g must only include a single oscillation where k here, k is just the wave vector in the dual lattice to gamma, right? So in other words, if this g here involves more than one simple epsilon oscillation, beta will not be equal to w. Another example, because you cannot only have oscillations, we of course can also have concentration effects. So look at this particular example of psi, where you again take some smooth, say Gaussian or whatever, C0 infinity, compactly supported amplitude, which concentrates to a delta at the point x0. And of course here you have to take into account this normalization factor. Then what you can prove is beta is equal to w if and only if f is 0. Now that's of course not so good news, neither is this. It basically tells you that for beta equal to w, I mean, there are lots and lots of possible scenarios where the two measures will not coincide. And this, of course, tells you that in general, it seems that this limiting measure, of course, will not describe the correct classical limit, as does the Wigner measure. I recall to you, though, that the limit of the particle and current density, this you already know, is always correctly described by beta by taking the first two moments. So, in other words, it will only be higher order observables that you do not correctly describe in the limit. Okay. Okay, final example here, which is something you have already seen in Remy's talk. Let me consider what is called a semi-classical wave packet or a Gaussian, a coherent state. So notice the difference here in contrast to this example where I have a concentration effect on the scale epsilon. Here I have a concentration effect on the scale square root of epsilon. And I take into account also a simple oscillation. Then, in this particular case, everything goes well. In fact, you can show that w equals to beta equals to this delta in velocity or in momentum and in position space. So for these particular kind of wave functions, the two limiting measures coincide and in fact just form what one would call maybe a single classical particle in phase space. So that led us to the so that observation sort of led us to the conclusion that probably in this situation things are rather well behaved, and in particular we should be able to infer something on the on the Bohmian, on the classical limit of the Bohmian trajectories. And so this is the last result I'm going to show you. So in this particular case, so I mean, okay, some notation first. So let me call just capital X and capital P the true classical Hamiltonian phase-space flow obtained from this system. And assume now that my initial data of my Schrödinger equation is exactly of this form, as I showed you before. Now, of course, I recall to you from the talk of Remy that you can prove, of course, now that for all t, or at least up to Ehrenfest times, the true solution of the Schrödinger equation can be approximated by such a coherent state. I mean, if you just shift sort of the center of mass by the classical flow, and similarly, if you shift, I mean, or if the oscillations are also, I mean, obtained in such a way. So so that we have already seen yesterday. Yeah, right. And okay, let me also recall to you what this particular topology of local in-measure convergence. So we have seen it basically already before. The limit of the as epsilon tends to 0 of the measure of this set. So this again the Lebesgue measure. The only difference as before is that for every Borel set omega with finite Lebesgue measure, this here goes to 0. So then the following theorem holds, again some sufficient regularity assumptions which are most probably far from optimal. So there are two statements. So you assume now that your initial wave function is given as such a coherent state. Then the first statement tells you that for all times t, the beta equals to the omega equals to this classical particle, where x, t, and p of t are just, I mean, move with the classical Hamiltonian trajectories. More interestingly, though, if you allow me to rescale the Bohmian trajectories in such a way that I shift, so to say, the initial data by this shift here, so that I have like a capital Y epsilon this rescaled position position trajectory and z epsilon the rescaled momentum. Then in fact what you can prove is that these rescaled trajectories converge to the classical phase-space flow locally in measure on RT cross RdX. So this is in fact the result which is similar to a very recent result by Dürre and Römer, which is published in 2010, which proved convergence of the sort of only of the x coordinate of the Bohmian flow in a different topology. So they proved it in probability, so the topology is different. So if you're in comparison to this result, what we can do is we can prove also convergence of the rescaled momentum, which is nice. Due to our techniques, we don't need an a priori estimate on the time dependence. That is sort of maybe not so important. But what we can, I mean, if you don't like this in-measure convergence, you might want to think of it rather that if you have in-measure convergence, just you look into your measure theory book and quote the following result, that there will be another subsequence epsilon n such that this convergence holds almost everywhere in every, say, finite set, finite Borel set RT cross RD. So you have basically almost everywhere convergence of these trajectories to the classical phase-space flow. And to conclude my talk, I will sort of show you a sketch of the proof of this result, because it, I mean, of course, I sweep all the details like a priori estimates and so under the carpet. I only show you the three main steps, which because it's sort of nice to see how all of these concepts go together. So what do you do? I mean, you can consider the Bohmian flow. You can consider it again as just a family of vector-valued epsilon-dependent, I mean, vector-valued functions, for which you can again define a Young measure. Let me call it omega of t and, I mean, parameterized by t and y, So this is the Young measure associated to, well, this in fact this rescaled Bohmian trajectory is capital Y and capital Z epsilon. Then just by using the push forward formula for my beta epsilon, so you write this in the weak formulation. I mean, you use the test function, you just write this down in detail and pass to the limit. What you get from this is the following identity. The limiting Bohmian measure is equal to this integral of f. So f has been my, I recall to this is just the initial amplitude squared times this Young measure of these trajectories. And now, since you know exactly how this beta looks like, what you conclude from it is that in fact this Young measure of my trajectories is nothing but a delta centered at p of t, I mean the classical momentum and the classical position. And now you just look again into your Young measure book or your measure theory book, which tells you that if a Young measure is concentrated in a single point, this is in fact equivalent to have to in-measure or local in-measure convergence of the sequence. And sort of this proof or this sketch of the proof tells you how you can sort of how all of these different concepts go together. And well, here's the conclusion. What I have shown to you is we have rewritten the Bohmian mechanics in a Lagrangian rigorously. I mean, in a Lagrangian form by using this Bohmian measure. Okay, we showed that they in fact solve a Vlasov type equation in a distributional sense. They incorporate the classical limit of the position and current density, quantum mechanical position and current density. They are, however, in general different from the Wigner measure. And yeah, in the particular case of semi-classical wave packets, in fact, the Bohmian phase-space flow converges to the classical one. But I insist on the fact that seems to be a really special case. I mean, just by recalling the examples that you've seen before, it seems highly doubtful that the limit of the Bohmian flow will in fact converge to the classical trajectories. I mean, of course, this is sort of a meta statement. There's no proof, but anyway, thank you for your attention.
Questions or comments?
So what about the limit of the second order moment in these examples you discussed?
In fact,
but it's the first question. The second question is, what is the meaning of energy in the Bohm picture? I mean, the second order moment is not conserved, I guess, right?
yes, so, okay, the second question I cannot really answer to you because I don't know what the meaning of energy is in this. I mean, clearly, I mean, there is of course, the energy you can always compute it from psi and, I mean, rewrite it in this form. What is lost is that it is not the second moment of this phase-space measure. So
this is a conserved quantity.
This is a conserved quantity, of course. About these examples, in fact, the theorems we proved them by showing that the second moments are different. I mean, these theorems that omega equals to beta is equal if and only if you can show. I mean, we prove this for the second moment. So in general, they are different.
Question?
In fact, the same question. Finally, if I understand, define the Bohm measure just in the first two moments.
Mm-hmm.
So that means that, for example, I can imagine that if you change slightly your wave function, you still keeping the same two first moments without changing.
That is very, very subtle because you know that from J. I mean, okay, if you allow me to sort of sweep the problem of nodes under the carpet, you know that from J, I mean from current density and from the position density, you can almost recover, I mean, the full wave function. I mean, you have the density. I mean, you take you compute the velocity field, which is then the gradient of the phase everywhere, but at points where the wave function is zero. So to change the wave function in such a way that the energy would be different, but the first two moments are the same, I think this is in general not possible. Or
Yeah, I was maybe not for general wave function satisfying the Schrödinger equation, but if you start for example from your example.
sure, but yeah, but then this but then you might say, what kind of insight do you get if this then does not solve your Schrödinger equation? No?
I mean, it's not linked with the fact that your Young measure version only looks at some special test class, because you always take x times y over x.
No, I don't think so. No. But I agree that there is a sort of a problem. I mean, also, just as Ingo said, I mean, it's not so clear what energy is in this picture. I mean, or kinetic energy. I mean, of course it's this, but it's not so clear how this relates to the phase-space flow, so to say. That is sort of this connection is somewhat lost.
I mean, in some sense, you have to look at it as a theory that recovers the first two observables in an x-axis, which, interestingly enough, it also does in the limit. And then, as Christof said, almost you can reconstruct the wave function from those two observables.
You mentioned that one of the motivation was for quantum chemistry.
Mm.
So in classical situation like hydrogen atom, what does it give? And what do you have to do to get to n-particle systems?
Well, I mean, what it gives, I cannot actually tell you. I mean, I don't know exactly what the chemists do, but what they do, as I said, I mean, they basically take these. I mean, what they typically do is they take Gaussian states, coherent states, and then they propagate their center of mass and their oscillations by this phase-space flow, and basically by just, I mean, setting the epsilon to 0 or different from 0, they say that they solve, I mean, either classical or quantum mechanical particles. Now, to which extent this is, I mean, on a Monte Carlo code and so on, to which extent this is a valid, I mean, numerical simulation, I'm not so sure, but I don't want to argue with the quantum chemists about this.
I mean, maybe you could add that it is a very tricky numerical task to solve those trajectory kind of ordinary differential equations. And I mean, you have to compute 30 derivatives of.
I mean, she will tell you more about this.
She had some very bad experience with it. It's really an extremely unstable process. I think we are not advocating this as
it's just
solving the Schrödinger.
It was just sort of as a motivation to tell you that, I mean, people actually use these things. I don't know exactly how, I mean, but yeah.
One last question.
You have to assume that rho has no zeros.
No.
So you can have vortices.
Yes. But the price to pay is these sort of almost everywhere statements that I have to do. I mean, all this flow, I only know it's defined, morally speaking, rho 0 almost everywhere. So what this tells you is that, I mean, I can't give you information about each single trajectory, or I mean, I can't tell you what happens when a trajectory goes into a node or at a 0. But
except you know that it doesn't happen very often.
Yeah, right. That's what
it
it
is.
Yes, in this sense.
So let's thank Christof again.